So, our second unit, Lesson 1, Force Concepts. A force is a push or a pull. That's a bad definition. That's the wrong definition. If you go down to the quantum level, we say that a force is an interaction between two subatomic particles. I think it's the baryons that transmit force. Maybe it's the leptons. I can't remember because I haven't done much quantum physics. We're not going to go down to that level. But I do always have to point out, Taylor, everything that we're going to be looking at this unit is going to be almost all wrong. There is no such thing as a normal force. There's no such thing as friction. There's no such thing as any of those things. There's only four fundamental forces. The four fundamental forces are the strong force and the weak force. Those are what hold atoms and nuclei together. Those are what let you be you. Then there is the electromagnetic force and gravity. Those are the four forces. Gravity is the one that you're most familiar with. Gravity is the one that's by far the weakest. Behold, ladies and gentlemen, I shall overcome the force of gravity. There's a magnet sitting on that chair. What are the forces acting on it? Get the obvious one. Watch. There, I overcame gravity. Gravity is about 1 billion times weaker than the other forces. It's the one that dominates your life because you're used to it so much, but it's actually really, really, really small. It's small enough that, for example, later on this year when we look at particle colliders and we look at electrons, electrons have so little mass, we'll ignore gravity because it's not going to make a difference at all. It might to like the 40th decimal place, but who cares? Force is a vector, and it's measured in units called newtons. Named after a scientist whose last name was? Very good. And forces are based on interactions between two objects. Some important forces we're going to study include the following. Hopefully you remember most of these from last year. Who remembers, what did we call the force that could be described as the Earth pulling on all objects in the downwards direction towards the planet's center? And my symbol for gravity was F with a subscripted G. This is also called weight. Who remembers, what did we call the force that could be described as microscopic hills and valleys between an object and a surface that interlock and prevent or impede sliding? Okay. And this is one of the few times where I write an extra letter. Oh, by the way, these are technically vectors, so I should put a vector symbol above all of these, shouldn't I? Most textbooks will call it F and then a subscripted F. I don't know why, but for years I've put FR, and it's one of the few times where I'll actually write one more letter than required, but it's part of me, so it's never going to vanish. What did we call the force that could be described as a surface pushing up on objects and keeping objects from sinking into that surface? It was also called the apparent weight of an object. Called that the normal force. It's a tricky force to wrap our brain around. Don't write this next bit down. Some textbooks will use a big capital N. Don't write that down for normal force. The problem is now that's north and newtons and normal, all of which can appear in the same question. So even though probably it might be technically wrong, I'm going to call it F with a subscripted N. Why did we call it normal? Does anybody remember what the word normal meant? No? Okay, we'll talk about that later on in the lesson. What was the force that could be described as the force that a stretched string or cord or rope feels when you pull on either end? Tension? Some of you might be feeling some next class when you're writing my test. This is where I really am wrong. I've debated changing my teaching. For years, Zach, I have always used a capital T for tension. That's wrong. In fact, it's going to later on this year, we're going to use a capital T for something else. The period of an object going around a circle, for those of you who are wondering. I really have debated, Haley, changing this to F with a subscripted T, and I may do that one of these years. Just means I'd have to go through my answer keys and change that too, which would be a bit of pain. What did we call the force that could be described as a contact force from an outside or external agent, usually a person, something coming from off the page? That's what we call the applied force. That's when I don't want to bother making up a story to explain what that force is coming from off the page. In fact, often this year, you'll hear me describe it as a little invisible angel, especially when we're looking at microscopic or subatomic issues where it's not a person, it's something so small. I'll say, pretend there's a leprechaun or an angel or something applying a force here, holding it up or lifting it down. What was the fancy word for the force of resistance from the air? It always acted in the opposite direction of motion. Now, I know air resistance is the 2-word answer, but there's a 4-letter word that starts with letter D that you could also use. Drag. Having said that, though, I think I almost always wrote it as F-air. And in fact, we're going to treat, Angela, air resistance much like friction. I went on this rant last year, but I'll repeat myself. Air resistance is a really tricky force because as you speed up, it gets bigger, which means now you'll slow down, which means it just got smaller, which means now you'll speed up, which means it just got bigger. You really need calculus to deal with it properly. The last one wasn't actually a force. It was the name that we gave to the total or the vector sum, the resultant this year, of all of the forces acting on an object. We called it F something. And letter N. Net force. This year, because we're going to be looking at more complicated free body diagrams, that will become more important. Now we go to Newton's laws. Got to go on my Sir Isaac Newton rant. Sir Isaac Newton, the reason we hold him in such high esteem is really, if you made a top 5 list of the top 5 mathematicians in history, he'd be in the top 5, maybe at the top. If you made a top 5 list of all the scientists in history, he'd be in the top 5, maybe at the top. There's very few people that are on both of those lists. Einstein would be near the top of the scientists. Not a great math guy. Other people might be on the top of the math lists. Not great science people. And I went on this rant this year. I'm going to have to pause the YouTube video because I'm going to be walking around. Sorry, folks. Newton's first law typically says something like this. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. What? Blech. Here's what it really says. The only way that you can accelerate an object or change its velocity, because that's the definition of acceleration, is to apply an unbalanced outside force. In other words, remember, since acceleration is a vector, it has both magnitude and direction. If an object is changing its speed or its direction, there's an unbalanced force acting on it. Instead of saying speed and direction, I'll just say if an object is accelerating, there's an unbalanced force acting on it. If it's not accelerating, the forces add to 0. The net force is 0. Zach, is there a force acting on you right now? Get the obvious one. Gravity. Are you sinking into the ground like quicksand? Are you flying into like Superman? Are you accelerating? No. So the net or total force on you right now has to be, this is how we deduced that the ground must be pushing up against you. This is how we came up with that idea of a normal force. It was a consequence of Newton's first law. Now, it's also often called the law of inertia because objects with lots of inertia, lots of mass, tend to resist a force. Let me give you a simple example here. Pause for a second. Newton's second law, which is, I think, the page across on the first page because this thing photocopied weird. It's the mathematical equation. F equals what? That's Newton's second. Although I think I taught you this last year, and I'll emphasize it a bit more this year. Newton was much more interested in acceleration, so he actually got the A by itself. And actually, he wasn't even interested in acceleration. He was much more interested in change in momentum and impulse. So he phrased his equation slightly differently. But we're typically going to go F equals ma. We'll explore this more later. Really, it's going to be the theme of the rest of the unit. We're going to find new and clever ways to write F equals ma. But look up. This year, look up. I'm going to be a bit fussier. It's really F net. The net force equals ma. And by net force, what I really mean there is do all your winner minus loser, combining everything, except now we'll have vectors and things as well. Newton's third law. It's often called the law of action-reaction. It's usually stated something like, for every action there is an equal and opposite reaction. How did I phrase it last year? Forces come in. If I want to write it as an equation, the force of object A on object B is the same but opposite, negative, the force of object B on object A. So just this part allowed us to already come to some conclusions. Why would an athlete, a sprinter, want low mass shoes?
Less mass, more acceleration.
I like the way Pat phrased it. A equals F over M. Let's suppose you've lifted weights and you've maximized the force that your legs can put out. What else is there in that equation? You can make M smaller. And if you divide by a smaller number, what happens to A? What happens to the answer? If you divide by a smaller number, yeah, if the number on the bottom gets smaller, your answer gets bigger, more acceleration. Okay. Why don't they run barefoot? Because wouldn't that be the logical next step? Not on a professional track. We could sweep the track off. What? Because we're going to talk about this later, but you might recall from last year, when you walk or run, what force is it that pushes you forwards? It's friction, because you actually push backwards with your feet when you walk or run. So it's a balance. Probably honestly, I'm waiting for somebody to design some kind of a rubber sole that you can glue to an athlete's foot temporarily and have nothing else. That would be the ultimate way to go, I think. Don't running shoes provide what? I know that right now studies are suggesting that the Western version of shoes with high arch support actually damage our feet. There's an argument like that things like plantar fasciitis and a lot of the Western foot problems do not exist in third world countries where people go barefoot all the time. And so there's a movement to embrace barefoot running. I'm waiting for somebody in the Olympics or wherever at that high level to design basically almost like a roll-on liquid sole that you put on someone's foot that stays for one race, gives you friction, gives you almost no mass. Be willing to try it. We come to our thought experiment number 2. Let's suppose that Patrick and Jaden are astronauts in an International Space Station. And Patrick picks up an object with a lot of mass, let's say a big food container, and he floats it down the hallway in the space station. It drifts down the hallway in 0G, and Jaden, rather than catching it, decides to stop it with his face. Will it hurt? Or the way I phrased it here, would it hurt to get hit in the face by a moving object while in 0G? Zach says yes, convince me. Okay. So? Yeah. So we'll combine both your answers. Object has mass, because mass does not depend on gravity. Mass is a measure of really the number of atoms an object possesses. And when it hits Jaden's face, would its velocity change? What's a fancy word for change in velocity? It begins with letter A. Also has acceleration. Therefore, force is applied to the face. It'll hurt. It's got mass, it's got acceleration, apply force. Pick your pencils up, here we go. A force with which you have had some experience is the force of gravity. Except the force of gravity between you and the earth has a special name. We call it weight. And it's measured in newtons. Weight is not measured in kilograms. Mass is measured in kilograms. Weight is measured in newtons. Or in the old system, pounds. Pounds was not a measure of mass. Pounds was a measure of force. The force of gravity is not the same thing as mass, although they're related. Mass is the amount of matter in an object, measured in kilograms, or in the old system, slugs. What a stupid system. To relate mass to force, what we really need to know is how many newtons are acting on each kilogram due to gravity. We have a fancy name for that, and this is a phrase we're going to be using an awful lot this year. We call it gravitational field strength. When you're in free fall, when you're in free fall, what's your acceleration if we ignore air resistance? If we ignore the negative, because that's directional, what's the magnitude of the acceleration? Units? The reason you accelerate down at 9.8 meters per second squared is because the Earth has a gravitational field strength of 9.8 newtons on every kilogram. If Earth had a gravitational field strength of 6.3, we would accelerate at 6.3 meters per second squared, because every newton of force every kilogram of mass feels that many newtons of force acting on it. The gravitational field strength, and we're going to learn later on this year how to calculate it, and then we'll start to leave the Earth and go higher and higher up, where G is no longer 9.8, where G gets weaker and weaker and weaker and weaker as you go further and further from the planet. Or you may have wondered, and we'll actually calculate it this year, how did they know what G was on the moon before they went there? Because they must have had to known how strong gravity was on the moon to design the rocket ships, the lunar landers that landed on the moon. You wouldn't have just guessed. There must be a way to calculate it without dropping an object and timing it. And there is. So the Earth has a gravitational field strength of about 9.8 newtons per kilogram. The moon's is about 1.6 newtons per kilogram-ish. You don't need to memorize the moons. If I ask you a moon question on a test, I'll give it to you. I think in the homework, it does ask you a moon question. There, the moon G is right in your notes. So we have this. Fg equals mg, where really this is called weight, and this is called gravitational field strength. G of Jupiter, gravitational field strength of Jupiter is around 22. That's why you feel heavier on Jupiter. G of the Sun, it's awkward because the Sun and both Jupiter and the Sun don't really have a surface to stand on, so it's kind of arbitrary where you do your measuring point, but G on the Sun would be much larger. And as you got close to the Sun, it would be much larger before you hit the Sun. Find the weight of an object A on the Earth, B on the Moon. Weight is another word, a synonym for Fg. And in both situations, it's calculated by mg, except on the Earth, we'll use G of the Earth, and on the Moon, we'll use G, little g, on the Moon. The mass in each situation is 10. Taylor, what's G on the Earth? 9.8. 10 times 9.8 is 98 newtons. So a 10 kilogram object, if you're holding it on the Earth, it's pulling down on your hand at 98 newtons. Taylor, what's G on the Moon? It's in that paragraph up there. So 10 times 1.6. On the moon, that 10 kilogram mass would be tugged down with 16 newtons. And that's why objects feel lighter on the moon. They have less weight. Same mass, less weight. Now turn the page. Example 3 says, select the best answer. Hey, we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. It says this. If the force of gravity acts on an object, then the object, A, remains at rest, B, moves at a constant speed, C, accelerates in the direction of the force, or D, all of the above. Kieran's thinking. Good. You ready? If gravity is acting on an object, then the object, who says A remains at rest? A. 1. B moves at a constant speed. C accelerates in the direction of the force. 1, 2, 3, 4, 5. D, all of the above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, if D is right, really all we need to do is give a situation where A could be right, where B could be right, and where C could be right. Give an example of each of them. Then it must be D. Let's try that. Because, by the way, I'm pretty sure it is D. Can you give me a situation where gravity could be acting on an object, but it remains at rest? You okay with that? So, Haley, I absolutely agree. A is right. Except it's not. There are other possibilities, too. Can you give me a situation where gravity could be acting on you and you're moving at a constant speed? Oh, you even came up with the nerd word, candy for you. What was it? When I jumped out of an airplane, although I initially accelerated, once I hit terminal velocity, once the force of air resistance exactly matched the force of gravity, I was moving at a constant speed. A terminal speed, but a constant speed. Or after I opened my parachute, gravity was still acting on me, I was moving at a much lower terminal speed, a survivable terminal speed. Give me an example of situation C, where I could be accelerating in the direction of the force. That's accelerating in the opposite direction of the force. I mean, I'm going to say this. Free fall, and I'll even put in brackets, in a vacuum. Technically. That gets rid of the terminal velocity situation. You recall last year I showed you a video of a massive room where they pumped the air out, and then you saw a bowling ball and some feathers fall, and in the vacuum, they both fell at exactly the same rate. What rate? 9.8 meters per second squared. Why? Because they were experiencing 9.8 newtons of force on every kilogram. I also should make sure I answer the question. Therefore, D. Newton's first law says that if we have balanced forces, objects at rest tend to remain at rest, and objects in motion tend to remain at motion. Blah. Newton's first law says this. If we have balanced forces, the acceleration has to be zero. That's the best way and shortest way to describe objects will remain at rest or remain in motion. Acceleration will be zero, which means you'll either stay at rest if you are at rest, or you'll keep going in a straight line, that takes care of the directional component, at a steady speed, that takes care of the magnitude. You okay with that, Mobeen? Oh, if we have unbalanced forces, then A won't be zero. That's the shortest way to phrase Newton's first law. Force is balanced, A is zero. Not balanced, A can't be zero. So we're going to start talking about the net force, or F net. And I need to point out that F net, put a little star here, Fnet does not appear on a FBD. What does FBD stand for? Okay, because Fnet is the combination of all the forces on your free body diagram. If you actually also put Fnet on your free body diagram, what you've just done is doubled the forces, because you've listed all the individual ones which make up Fnet, and then you've also put Fnet. You put twice as many forces as necessary. So don't do that. Fnet never appears on the free body diagram. Where does it appear? It'll appear on the right-hand side on our equation when we go winner minus loser equals Fnet. Little note, these units are the same. Newtons per kilogram is the same as meters per second squared, because acceleration is also force divided by mass. Newtons per kilogram. I got the A by itself in Newton's second law. So another term for acceleration due to gravity is gravitational field strength measured in newtons per kilogram. Oh, didn't start. Yeah, it did. Damage your self-esteem with a lovely demonstration. We're going to pause here.